Hello, I'm your host, Grayson Brulte. Welcome to another episode of SAE Tomorrow Today, a show about emerging technology with the leaders and innovators to make it all happen. On today's episode, we're absolutely honored to welcome Craig McMillan, MGSE Growth Leader, GE Aerospace. On today's episode, we'll discuss how the industry-level forces are shaping the future of aerospace engineering, from safety standards to the emerging challenges of AI-enabled flight. We hope you enjoy this episode. Craig, welcome to the podcast.
Thanks, Grayson. I appreciate it. Glad to be here.
It's great to have you here. I'll just say it as a little kid, aerospace is cool. And there's a lot of moving parts that go into aerospace, but behind all the coolness is the kid in me, there's a lot of complexity, a lot of moving parts in aerospace. So the big question, Craig, is what role do standards play in enabling the complexities to turn into realities to allow this industry to scale?
Well, I think it does two things. The first thing is it gives a common reference for different companies. So there are multiple companies, Boeing, Airbus, for engine manufacturers, Pratt & Whitney, Rolls-Royce, GE Aerospace. We all make common products. And having these standards allows us to talk in a common language. So when we demonstrate to the regulatory authorities like the FAA and EASA, we can talk to them in a common language so the regulators don't have to learn the language from a bunch of different customers or from a bunch of different applicants. And then the second thing it provides is it provides a roadmap for handling the complexity, because our systems are getting increasingly complex. And by having a standard, you're giving a roadmap of the minimum acceptable criteria that everybody can follow to ensure that you deliver safe products. Because as cool as aerospace is, safety always has to be at the forefront of everything we do. And these standards gives a minimum bar to meet from a system safety perspective. And that's critical to ensuring that we have a safe and usable airspace system.
Where would we be? I like the term that you use a lot, common language. Would we have this manufacturer going this way, this jet engine company going this way, regulators saying, what, who, where, how, why? Is that what would be going on if there wasn't a common language?
Yeah, because each of the applicants would try to provide a package using their own terminology, and then the regulator would have to speak numerous different languages in order to understand what it is they were doing. So by providing a common reference, the regulators are more able to assess the compliance to the safety standards in a way that makes sense to them. And so standards like ARP4754 is not a standard, it's a recommended practice, but it gets invoked by advisory circulars and such by the regulatory agencies.
So where would we be without ARP4754B? Where would we be as an industry?
Well, we know where we'd be because we were there 40 years ago, or 30 years ago. So what that particular document shows is how to meet AC 251309. And that is the regulatory rule that we have to meet to show that we have a safe system and it doesn't do anything it's not supposed to do. For years, with simple analog systems, applicants were having trouble deterministically showing that they met a minimum bar of system safety. And as the systems got more complex, it became unmanageable. So what happened in the 90s is that we came out with this concept of development assurance. So when you cannot exhaustively verify a product, we developed a process by which you could show with a high level of confidence that a product was safe in accordance with 25.1309. So ARP 4754, now we're up to revision B, provides a roadmap to how you can show compliance to FAR 251309.
And sitting here as a non-aerospace engineer, how would you describe that in simple terms to a listener or the member of the public? It's okay, yes, you're all about safety, but how would you put that into simple terms so they can grasp?
Well, for instance, you break it down in terms of function. So an engine provides thrust. And you look at what an engine can do, there could be two forms of failures. One would be a loss of function, so you lose an engine. And so what development assurance says, okay, if I lose an engine, what is the impact on my aircraft and how would I mitigate that? In most cases, you would have second, third, or fourth engines, and you would continue to fly on the remaining engines. A second type of error that we try to mitigate is an undetected erroneous data. So let's say in your airspeed, you have you're flying at 150 knots, but your airspeed indicator shows that you're flying at 180 knots. It's not enunciating any sort of failure, but it's giving you incorrect information, but you, the pilot, don't know that. And so we developed a development assurance process to show that even when that sort of undetected error occurs, you would have a means of detecting that error and taking the appropriate action in case you would have two other airspeed indicators. And when two airspeed indicators are showing 150 knots and the third one is showing 180 knots, you could reasonably deduce that the third one is the erroneous indication and go by the other two. So we provided a mechanism for system safety to determine when these sort of known and unknown errors occur and how to properly mitigate and respond to them.
Does that change when you're looking at software versus hardware, or are they all interconnected?
So system safety applies to all the above, but when you get into system software, it gets more complex exponentially faster because with a take a flight management system, for instance, it has hundreds of thousands of lines of code in it. The amount of things that can go wrong in hundreds of thousands of lines of code is obviously a very large number. And so DO 178C was developed to provide development assurance for software, which feeds into ARP 4754B. And so you provide this layered approach where you have development assurance at the system level, and then you would do development assurance at your hardware and software levels, but it all ties together. Development assurance for aeromechanical systems like a flap, a spoiler, or something like that is a little bit more straightforward because you don't have the complexity that you would with the software, but you still have the important safety critical functions that you would need to evaluate.
And then you look at evaluation, where do environmental risks such as radiation or unknown environmental things that could happen, where does that come into the risk analysis?
So as part of the development assurance process in ERP 4754B, we have the safety assessment process defined in ARP 4761A. And that basically is a sibling document. And that's where we get into some of those types of common mode errors like bird ingestion, for instance, where you would fly through a flock of birds and lose both engines, like the US Air incident on the Hudson River. Or you would look at radiation effects like single event effects from radiation or any sort of environmental factor like that, like heavy rain or lightning or things like that. So that would be part of your risk assessment that you would do as part of your safety assessment.
As part of a risk assessment, does the industry share risks or edge cases that they've encountered with each other? Say, hey, we've experienced X, Y, and Z. This is how we resolved it. You might want to plan for that. Is there open communication on that safety level across the industry?
Yeah, that's fairly typical because we all have an interest in safety. When when there is an incident involving an aircraft, the general flying public isn't necessarily attuned to what aircraft manufacturer, what engine. It's just an aircraft accident. We all have a vested interest in having safety. System safety is never going to be a business differentiator. We all want to be safe. And so there is a lot of collaboration. So when we work on these committees to develop these documents, all of the companies that I mentioned previously are actively engaged, working collaboratively together, trying to make sure that we are all doing what's best for the industry from a system safety perspective.
Are those system safety teams, are they independent where, and I'm just asking this as an individual who flies, a boss can't say, nope, you're going to do this. Are they fully independent where they have the say and they cannot be influenced either by an internal person or an external person and they're just purely focused on safety?
Well, that certainly is the intent. How that is implemented differs from company to company. What is typically recommended from the regulators is that you would have a safety management system and that you would have independence of that safety management system where you could raise that issue. And so how that is applied is unique to each company or to each applicant.
From a safety perspective, obviously, we're very fortunate in this time of society. We have access to a lot of really great tools, simulation, digital engineering tools. When did those come into the picture from a safety perspective? When did those individuals and those safety teams and the engineers start to run different what if scenarios for safety planning? When does that start in the development process?
Oh, pretty much from the beginning. When you even initially conceive of a product, you would typically address those types of major concerns to ensure that you don't go down the path of developing something that then is not sustainable from a safety perspective. So those simulations would start on day one. Obviously, the initial simulations would be very high level with low level of detail, because think of it as like a back of the napkin calculation to make sure that what you're doing is appropriate. And as the design progresses, these simulations and analyses would become more and more refined and more detailed.
Is there let's say industry wide, not a standard, but a best practice where in the beginning, for a certain period of time, simulation is done before it takes the next step? You're trying to uncover things that you might have thought of and really kind of push the envelope, and then at that point, it graduates to the next step.
Typically, running simulations early helps find issues before you actually build hardware. And so it's in your best interest to run those simulations to validate your design before you go build it. You still have the verification process after you build the product to ensure that it does what it's supposed to do and only what it's supposed to do. But the simulations gives you higher confidence. There can be, if you find something after you build if you find an issue after you build the hardware, it's a very disruptive process to go fix it, because you have to go back and change your design, then you have to rebuild the hardware and then go back and re-verify it. Whereas if you find something in simulation, you just fix it in the design before you build the hardware and before you ever tested it on a test bench. So finding problems early has significant benefits on several fronts. And so obviously you want to run the highest fidelity simulation as early in the process as possible to give you the highest confidence that you're actually building the right product.
Have you seen, if just using industry averages, where a new product is in simulation for X amount of time? Is there like an industry average? Is it 8 months, 2 years that something sits in simulation before it graduates? Any data that you've seen?
It's all a function of the complexity of the product and then the computational methods. So it's ever changing. I mean, back in the day, they designed airplanes completely with slide rules. And now we're using supercomputers and high performance computers and all sorts of advanced computational techniques to develop these things. And it just seems like the systems become more complex in step with the increase in ability of computing power. So the computing power can never keep up with the complexity of the system. So we're always having to catch up to be able to analyze these systems. Think fly-by-wire and fully digital electronics, flying the airplane and things like that. Where back in the day where everything was a cable and pulley system, it was a little bit easier to analyze it, but you couldn't do as much with it. So a fly-by-wire flight control system is more capable than a cable and pulley system, but a cable and pulley system is easier to analyze.
Do we ever get to a point where it's too complex?
I don't think it gets to the point where it's too complex. It would just take longer to analyze it and be able to provide you the confidence that it's safe, because you simply just have more to analyze. And that's where digital engineering comes in, where if you have things represented in a digital form, then you would provide the means to be able to analyze it more thoroughly, more exhaustively using automated techniques, because everything is interconnected in a digital representation. So applying digital engineering with an increase in complexity is a very natural fit. Does that make sense?
It does. So then on the backside of that is, where does AI come into the equation, and how is the industry approaching models? They're using closed models, open source models. And I asked that from a data leakage standpoint. There's been a lot of government documents. There's been a lot of public documents around data leakage. So is that when AI enters the picture, then how is the industry thinking about it from a model's perspective?
The answer is, in safety critical systems in aviation, that's still an open question. So AI, we're still at the early stages of applying AI for the development of safety critical systems. As part of the SAE working group, we've started a working group to provide examples of how AI can be used in development of safety critical systems using the development assurance techniques. The problem with AI is it's not deterministic. If you give it if you give it the same input 5 times, you could conceivably get 5 different answers. And so we have this term called qualification of tools, DO 330, if you're familiar with the RTCA standard. gives a template for defining tools for software development. AI cannot be qualified because it won't give you the same answer. So you have to apply the development assurance approach and say, how can my AI introduce an error into my product? And how would I identify and mitigate that error? And so that's what we're in the process of doing now. So we're still very much at the early stages. AI is never going to replace an engineer, or never may be a strong term, but because of the limitations of the determinism of AI and the lack thereof, the human is always going to be a critical element of the design process. Now, the AI can help the human go faster, provided that the human is cognizant of the problems that an AI can introduce in a product, and the human is using the AI as an aid and not as a replacement.
That's an interesting approach because I could sit here and make an argument that the human could write a loop scenario and then build a validation layer that could accelerate it, and then the human just becomes the validator. I mean, that's where it's going, and non-mission critical software engineering, and it's amazing what looping's doing. Does that enter the picture at some point where the human just acts as that validation layer, and they wrote the loop?
I guess I'm not sure what you mean by a loop. A loop would be fairly deterministic. So we have tools that have been qualified for safety critical systems where you would develop a model of a product, and then you would auto generate the product using that model using a qualified tool, because that tool is qualified to generate the same product every time given the same inputs. So uh, I'm not sure about the loop example you gave, but if it was something more of a deterministic way, there would be a way to qualify that to when the human could give it the inputs, the loop would generate the outputs. And if it was a qualified mechanism, you could then rely on those outputs. With AI, that would be difficult to do because of the lack of determinism.
So from an AI perspective, do you see in the industry the companies making that decision, or is it at a best practice level? Is it a standard level, or is it at the regulator level? Where do you see those AI decisions being made in the stack?
Honestly, it's a bit of all the above right now. It's because AI is such a rapidly emerging technology, there isn't a lot of organization on that right now. And so we're trying to get our arms around it because everything is moving very quickly. So the answer is all the above. The regulators are trying to get their arms around it, the companies are trying to get their arms around it, and we're all working together. And that's why we have this working group to define using AI in the development of safety critical systems to provide some guidance to make sure that we don't get too far down the path and realize, hey, we did something here we shouldn't have done, because it's harder to go back and fix something once already done rather than getting it right the first time. So it's because it's such a rapidly emerging technology, the industry is trying to react to it very quickly, which is difficult when you have people from different backgrounds, from different companies, all trying to work together. And we all have the same goal in mind, but when you come at it from a different perspective, there can be different viewpoints, and those have to be resolved and develop a consensus.
If you look at some of the largest publicly traded aerospace companies, there's a common denominator there. A lot of them have contracts with the Department of War, and under Secretary Hegseth and DepSec, there is a large push towards automation inside of Department of War, towards autonomy, and the embracement of called sovereignty AI. As the Department of War puts these mandates out there, does that move this potentially faster since they are such a large customer historically to the industry?
So the Department of War would typically be on the leading edge of technologies like this when it comes to digital engineering and AI. And the civil side of it would be more cautious because obviously when you have the flying public involved, there's a higher standard. The military has more flexibility on what they deem to be acceptable than a civil regulator would have. And so, yes, there tends to be a lot of leading edge development on the military side. And then when it becomes more mature, it can migrate its way into the civil realm. But it's a rapidly emerging field right now. So we are seeing some of that. And so on the military side, you see a lot of AI with regard to things like swarming and collaborative combat. And so they are pushing the envelope on things like that. And some of that technology, when it becomes mature, may make its way in, but we haven't seen that yet. It's way too early to have seen any of that migrate to the civil side.
Well, I think it's definitely something to watch, and I want to get back to this here because the ARP 4754B recommends process independence between the engineers who capture the requirements and the team validating them. Why is that?
just to eliminate a common source of error. So if somebody is checking their own work, has there ever been a time when you wrote a document and you've looked at that document so many times that you would have an obvious misspelling and you would just glance right over it because you've seen it so many times? Whereas if you bring in somebody from the outside and somebody said, "Oh, you spelled red with two D's," and you looked at that document 20 times and never saw the error, that's an example of why you would want independence, because you want somebody with a fresh set of eyes looking at something, and it's all about confidence. So you would only apply that to the systems that have the highest criticality. You wouldn't do that to all systems. So, for instance, like a passive maintenance system that's only used after a flight is complete, you would need that level of rigor for the independence, because if there's an error in a maintenance system, it would only affect your ability to diagnose the airplane once it's on the ground, as opposed to something like a fly-by-wire flight control system, where if there was an error, you could lose control of the airplane. And so you want to avoid that single point of error. And having an independent reviewer who is also a qualified expert looking at the same work gives you higher confidence that a design error would not work its way into the product.
Well, it's a valid point. You could sit there and say the sheep went over the hill, and you could look at it 100 times. But if that sheep had an extra e, like you used the a, it's like your eyes would glaze over it. So it's almost like if you want to look at it as a verification layer, as another set of eyes. It's a really good thing. And then on the safety front, is so critical to aerospace. How should teams handle the open problem reports at the time of certification without compromising safety?
Each open problem report would have to be evaluated on its own merits, because some problem reports are just trivial things like fixing a header in the software code, which makes the code more maintainable, but it's not a system safety issue. Whereas other items are safety critical and would need to be addressed immediately prior to delivery. So each open problem report should be assessed for system safety impact. And if it's determined to be not critical to system safety, then that would be something that you could reasonably defer. But each one would be considered on its own merits. There is no one size fits all approach. And it's hard work.
Is there a committee that makes those decisions? Like, it's very similar to what you said with the second set of eyes for the A's, or is it just one individual that's making that decision?
Again, that's a company by company decision. Typically, you would have a change control board that would evaluate those, and you would have a system safety expert who is part of that board who would provide the system safety input. So rarely is it one person for safety critical systems.
Which is a wonderful thing, and you're doing really wonderful work with all the volunteering work you're doing on the SAE committees. Craig, what is the ultimate goal of the SAE S19 committee? What are you hoping to achieve?
So with the S19 committee, it's a digital engineering committee. And what we're trying to do is unify everybody to speak a common language, because we're all applying digital engineering and we're all sharing these models and eventually feeding these up into airframes. But we're using different methods to develop these models. So what we're trying to do is define a way, a common language to pull these models together, where models from different sources can be plugged together and used to demonstrate that we have systems that are performing as they're intended. So the terms we're using a lot are terms like ontologies and knowledge graphing. So if we develop a model in different languages, so say you've got like a SysML model versus a Capella model, well, they're all defining the system development. And so we know the terms in system development. We know the terms in development assurance. If these models can be mapped into an ontology to create a knowledge graph, we can connect them together to show that this square peg actually does fit in this round hole, because they are all accomplishing a similar function. And so that's what S19 is trying to do, is trying to unify the industry so we can still apply digital engineering in a way that makes sense for our companies, but then we can plug these things together in a way to make sense when they're all integrated into an aircraft or another type of aerospace platform. I guess I should be careful here because we're talking about aerospace. So we're talking about space vehicles as well. So it'd be more than just aircraft.
That's fascinating. Will that language cross borders? So right now we're both based in the United States. Will that go to the EU, to the Asia region? Is that
Yeah. So the S19 committee is a multinational representation of members. So it is primarily Europe, Asia, and America are the primary members right now. And I want to say Canada as well. So, so yeah, it's not just a US based team. It is a multinational team for sure.
Multinational, obviously, there's senses of pride. There's a lot of issues that go in, and the cultural issues. How, since it's multinational, do you get all individuals to buy into the common good, the common language, or is it a lot of negotiation? Like, what goes into actually making that a reality?
We all want the same outcome. We want to be able to share we want digital models to continue to develop because digital engineering, given the level of complexity of the system, is a necessity going forward because using a document centric system to maintain systems of this complexity that you referenced earlier is just unmanageable. And it's not going to impact system safety. It's just going to make these things so difficult to maintain that it's going to be an unrealistic time frame to be able to document and analyze these systems, whereas digital engineering would give you the way to develop and analyze these systems much more expediently, pardon my language. So we all have a common goal, but we all have different viewpoints. And that's what makes working on these industry committees interesting, is that we are all trying to reach a common ground coming from very different viewpoints. And so sharing those viewpoints, speaking a common language, and then getting to a consensus outcome is a necessity, but it's something that takes a lot of work and a lot of investment from all the parties.
Yeah, a lot of time. You volunteer your time. The other individuals volunteer their time. I'm thinking about digital engineering. I look at this. Okay, it has the potential to increase safety, but then also has the potential to unlock scale, which benefits all of the companies. How do you balance all of the potential outcomes that could come out of this to ensure that obviously safety is at the forefront, but something else doesn't try and displace it in terms of the stack?
Well, that's where leadership comes in. You got to have clear goals, clear priorities, and the leadership has to provide those priorities and keep people aligned moving in the same direction because sometimes you have to make some calls to say, hey, this is a lesser priority. We're going to put that on the back burner. You want everybody to have a voice. You want everybody to have a chance to share their opinion, but you can't do everything at once. At some point, you got to make some calls, and a strong leadership is essential to any well functioning committee.
And leadership is what drives the companies that makes this all happen, and it enables us to go from New York to Joburg or New York to Athens. It allows us to happen and to get there safely. Putting that all together, Craig, what is the future of aerospace engineering? Because as a consumer, I love it because I'm able to go safely from all the way around the world. But you're here building it. What is the future of the engineering side of it?
Well, it's a pretty broad question. And if I truly understood it, I could be a very, very rich person. So I think you alluded to it very briefly there by saying going New York to Johannesburg. One thing that's happened in the industry so today is Tuesday, July 7th. My 36th anniversary in aerospace is Thursday, July 9th. And in my 36 years, the one thing I've seen is a change in the way that air travel has occurred. Back in the day, it was the hub and spoke system. And so everything went through New York, Chicago, LA. And now you're starting to see more of these city pairs that are more unusual, like Dallas to Madrid, for instance, or I'll just pick a random one, Las Vegas to Xi'an, China. And so because these routes become longer and thinner, it's putting more demands on the design of the airplanes. And so I think we're still continuing to push the boundaries of what we can do. When you see companies like Boom Aerospace out there, we're pushing supersonic travel. And so we could potentially get to the point where you would fly on these long flights in a matter of hours, just a few hours, as opposed to 10 plus hours. Like LA to Sydney is what, 14 to 16 hours, depending on conditions. And so supersonic could be a big part of that. The problem that we saw with supersonic, going back to the Concorde days, is a way to make that economically viable because the cost per seat of a supersonic flight was prohibitive in the early days and required a lot of subsidy. And then when that became no longer sustainable, that supersonic travel stopped. And so there are continuing to be evolution of those type of technologies. You're starting to see a lot with autonomous travel. So you've got companies like Joby and Archer that are pushing the limits, or they're expanding the boundaries of autonomous travel. So I could fly in a local metropolitan environment instead of taking a taxi cab or an Uber that would take me a couple of hours. I could get this autonomous taxi that could get me there in 5 to 10 minutes. Again, that's a case where technology is pushing the boundary of what's possible, but we would have to do so in a way that would be economically feasible, because obviously these things can't be sustained without some sort of viable economic plan. These can't be supplemented by government assistance forever. Sometimes you can to get them off the ground, but they would have to eventually stand on their own.
They have to stand on their own. Then you're starting to see the trend now, the long flights out of Sydney over 20 hours. You have the New York to Singapore flight over 20 hours, where these companies, or Singapore Airlines and Qantas, are trying to go further. And then you're right with Supersonic and Joby and Archer. It just seems that we're going into the golden age of aviation, where everything is changing, and when it changes, it opens the world. If we can go from New York to Sydney in 4.5 hours, that's a game changer. Or you can go from New York to London in 3 hours. That's a game changer. You just go there for dinner and come home. It really opens up the world and opens up really great experiences. And that's the beauty of aerospace. Craig, as we look to wrap up this insightful conversation, what would you like our listeners and viewers to take away with them today?
Well, the number one thing is safety is the top priority, full stop. Everything we do starts and ends with system safety. Our priority is to make sure that air travel is safe. And many of us spend our careers working diligently to make sure that is the case. And it doesn't matter what company people come from, that is always their driving focus. So that's the number one goal. And we get into aerospace, as you mentioned earlier, because a lot of us just simply have a fascination with flying. And so there's a lot of passion that goes into what we do. And we want to do what's best for the flying public. We want to make sure that we have safe products. We want to have products that do what people need. You mentioned the future of aerospace before. You're starting to see now that going into space now has some potential commercial applications. Virgin Galactic, SpaceX, and then Blue Origin. We have commercial ventures that are now trying to get off the ground, try to make space travel something that people would do in their lives. And so the boundaries are expanding, but we're always trying to expand these boundaries in a way that's safe. And we mentioned supersonic travel. The Concorde had a couple of events where they had a tire burst and they lost an aircraft because they blew a tire and it resulted in the loss of the aircraft. We never stop thinking about those types of things. So every time we push the boundary, we are always centering on system safety to make sure that when we push the boundary, we're doing so in a way that's sustainable.
Unfortunately, Stanley Kubrick's version of 2001 with Pan Am taking us up there is not going to happen, but it will be an aerospace in the future that will take us to space. And as a society globally, we'll never stop investing in building aerospace. It's what connects us all. Today is tomorrow. Tomorrow is today. The future is aerospace. Craig, thank you so much for coming on SAE Tomorrow Today.
Right, thanks, Grayson. I enjoyed being here. Appreciate the interview.
SAE International makes no representations as to the accuracy of the information presented in this podcast. The information and opinions are for general information only. SAE International does not endorse, approve, recommend, or certify any information, product, process, service, or organization presented or mentioned in this podcast.